So the plate starts moving at t equal to 0 with a constant speed u naught in the x1 direction, and as I was saying, we will look at uniform flow in x1 direction. So now uniform flow assumption is stronger or stricter. Uniform flow assumption is stronger or stricter than the fully developed flow assumption. In fully developed flow, we had assumed that the flow velocity is not changing in the x1 direction or the flow direction. When we say the flow is uniform, we're not making assumption just about the velocity but about pressure as well. So this means u and p are not functions of x1. Okay, they're not functions of x1. So there is no variation in any quantity in the x1 direction wherever you say that the flow is uniform. Another word for this is usually homogeneous flow in x1 direction, but we will not use that till we get to some later chapters. Okay, so uniform flow in x1 direction is the assumption that we are making, and that's pretty much it. That is the and we'll make a planar flow assumption as well. So planar flow. So these are the two assumptions that we are making, and based on this, so this is a hard wall that you see. So using continuity equation, and the uniform flow assumption, we again obtain that u2 is constant. Okay, we obtain that u2 is constant, and this would mean since u2 equals 0 at x2 equals 0 for all times, this means u2 equals 0. Okay, technically u2 is not a constant because this time, as you can imagine, that the flow was quiescent at t equal to 0 and suddenly the plate starts moving. Okay, so you cannot assume the flow is steady anymore. So technically from here what we get is that u2 is some function of time. Okay, and we say that u2 is 0 at x2 equals 0 for all times, so that would mean u2 is 0 for all times. Okay, because it's not a function of x2, so why would it be varying at other times? If I can determine its value at one x2, it's the same at other x2 values. Okay, so u2 equals 0 for all times, and this is how we obtain the fact that this is a unidirectional flow. Okay, that the flow is happening in only one direction. Now from u2 equals 0, you substitute this in the x2 momentum equation and you would obtain del p over del x2 equals 0. Okay, from our uniform flow assumption, we know that del p over del x1 is also 0. Okay, so p is just a constant, or it could be a function of time, but it doesn't matter to us because these quantities are 0 anyways. Okay, these quantities are 0 anyways, and these are what appear in the Navier-Stokes equation. So this gives an important intuition that this absolute value of pressure, it may be fluctuating in time, but if it is fluctuating uniformly everywhere, then it doesn't matter to the flow because it's the derivative of pressure that appears in the momentum equations. Now let us substitute this in the x1 momentum equation and we will get okay, we are looking at planar flow. Del u1 by del x1 is 0 because of our uniformity assumption. u2 is 0. We are looking at planar flow, so this guy is 0. This guy is 0 because of uniformity. This guy is 0. And we know that del p by del x1 is also 0 due to uniformity. So, the eventual equation that we are left with is this. Okay. So, we have an unsteady equation, we have an unsteady partial differential equation at our hand. Usually in textbooks you will see this written as an unsteady heat equation. Okay. This is your unsteady conduction equation, and the intuition of this equation you can gather is, so let us say you have, let us say I write this equation for some variable t. Uh, let us say I write this equation for some variable t and x, and this is your t, this is your t at time equal 0. Okay, at small time t equal to 0, small t equal to 0, this is what our capital T as a function of x looks like. Okay, and now the equation is saying that del t by del t is some constant alpha, say this alpha is positive, is some constant alpha times del 2 t by del x square. What is del 2 t by del x square? The second derivative here, positive or negative? Negative. What about here? Del 2 t by del x square? Positive. Okay, so at the troughs it is, at the crests, what are they called? I don't know. What is this one called? Crest or trough? Trough. So at the troughs these are positives, at the crests these are negatives. Okay, so this means, so if del t by del t is negative, that means this t variable would be decreasing. Okay, so here the t variable would be decreasing, here it would be increasing. So at later times you may find that this is what happens to your capital T field. So any undulations in the capital T field, this equation is trying to kill them. It is trying to kill, or as it's called in physics, it is trying to diffuse those undulations, it is trying to diffuse those perturbations. Okay, so there is an effect that happens on every undulation because of its second derivative. Okay, now think about another heat transfer equivalent of this. Let us say you have an infinite slab of some material and you have a temperature here, and you suddenly raise the temperature. So this slab is at temperature T naught and you suddenly raise the temperature as Th. So at time t equal to 0, this is what your plot of T will look like. There is a sudden rise in temperature here, and everywhere else it is T naught. Okay, so this is like a very strong undulation. Okay, this thing will diffuse into the slab. Okay, and this diffusion is happening due to this second derivative. Okay, that is the intuition for this equation, the unsteady heat equation. So as you will see that this is exactly what happens in our case here. The fluid is at rest and suddenly we move the plate, we start moving the plate, and after that the plate is moving at a constant velocity u naught. So the flow, there was no flow and suddenly there is a flow of, there is a velocity of u naught at x2 equals 0. So this velocity or this momentum, it diffuses upwards, and this is the equation that is governing this diffusion. The momentum is diffusing upwards. Okay, and so we will solve this equation with the intuition that momentum is diffusing upwards. Okay, so from now on x1, x2, x3 if I am using, I will just write them as x, y, z. Okay, and u1, u2, u3 I will write them as u, v, w. Okay, just to give an intuition of what is going on in the x, y, z directions, and it is, at least to me, this is easier on the visualization. So this equation is essentially del u by del t equals nu del 2 u over del y square. This is the equation that we have to solve. What are the boundary conditions? So this is a second order PDE in space and first order PDE in time. So the boundary conditions are u at y equal to 0 for all t is u naught. Okay, u for y tends to infinity for all t is 0. What we say is that the fluid above the plate is extending all the way till y tends to infinity. Okay, and the effect of the plate moving takes an infinitely long time to reach there. So, for any finite time, what we say is that for y tends to infinity, for any finite time the velocity is 0. Okay. And the initial condition is that for all y at t equal to 0, there is no flow, there is no velocity. So, we have two boundary conditions, we have one initial condition, and we can start solving this equation. There are multiple ways to solve this equation. Okay. There are multiple ways to solve this equation. One is you can use a Laplace transform. Do you guys know what is a Laplace transform is? Huh? You guys know what a Laplace transform is?
Integral where you multiply e to the power minus st
Hmm.
to the function.
Have you used it in any other course? Controls?
Control.
Huh? Are you from Mac? Oh, okay. What about ECM guys? Anyone? I mean, is it covered in your math courses? The Laplace transform is covered in your maths course, right? First year, yeah. So you can use the Laplace transform technique. Okay. So the idea is that we define this as the Laplace transform of this velocity variable, and it's a function of s. Okay. And from here you can show that Laplace transform of del u by del t is simply s times this u. There is a e to the power st, not minus st, I think. Okay. So there is a, or is there a minus st? Yeah, it's a minus st. So there is a, the del u by del t has a Laplace transform of s times capital U. So you can show that s times capital U equals nu del 2 capital U by del y square. You can solve this. Okay, you can solve this and do an inverse Laplace transform. Do you guys know how to calculate an inverse Laplace transform? Huh?
Plus.
It's a plus. Okay. So do you guys know how to calculate an inverse Laplace transform? Do you guys know how to do complex integration? Residue, using the residue theorem. Have you covered that in your maths courses?
Typically, the class transform is like we have to know the inverse transform.
No, so that's what is usually done in Maths 1 and Maths 2 courses in Laplace transform. Have you covered complex calculus? You have not covered complex calculus? Do you not know Cauchy-Riemann equations? It was covered, no? So at least it was covered. Okay. Cauchy-Riemann equations you don't know? Riemann integral is different. Cauchy-Riemann equations for complex functions, complex valued functions of complex arguments you have not covered.
I checked it's e to the power minus st.
Okay, yeah. So the way inverse Laplace transform is defined as is 1 by 2 pi I integral capital U y comma s e to the power st ds. Okay, and where this integration, as you can see, this is an improper integral. The units are from infinity, minus infinity to plus infinity in the complex plane. Okay. So usually when you have these kind of integration limits, then what is done is you have to do a contour integral. But if you guys don't know about residues, complex calculus and those things, then I guess these things are irrelevant to you. But it is very surprising that you guys don't know complex calculus. I mean, what kind of
This was done in
future?
control system.
Yeah, but it should be done in maths 1 and 2 courses. It's not a controls is application of this. Now this is actually, I don't know.
So in the initial condition, can you also have ux at t is equal to 0?
U
U of x. for all x at t is 0.
But that's not an initial condition, right? Because your independent variables are just y and t. You need conditions in y and t, not x. X is irrelevant because the flow is uniform in x. Okay. So I don't know, maybe look at Krasig's textbook and go through the complex calculus part, because otherwise this course is not going to be very uh, easy for you guys. I mean, we can have alternative solutions, but the thing is Laplace transform method offers a direct way of solving most of the unsteady equations. Most of the unsteady equations we can just try to use Laplace transform and get to some result. Otherwise, it's like a combination of different techniques which you have to apply for different problems. This is one, this is like one hammer that hits all nails, but otherwise you have to look at different type of techniques. So we'll look at the other technique for this equation, which is called the similarity solution. So similarity solution is basically an interesting solution, an interesting way of calculating the solution, and it works when you have domains which are infinite or semi infinite. So here the domain is bounded at y equal to 0 and unbounded for y greater than 0. Okay, so this is a semi infinite domain. Okay, an infinite domain would be from minus infinity to infinity. Okay, in both of these cases you have these solutions called similarity solutions, where we get an intuition that, let's say you have this as a solution of the equation, then let us try to ask the question, what about this guy? If I scale my y with square root alpha and I scale my t with alpha, then what about this guy? Is this guy also a solution of the equation? So we try to find out. So del u by del t becomes, so what will it become? So del u by del alpha t times del alpha t by del t. So this is alpha times del u by del capital T. Let's write this as capital T, this as capital Y, and then del u by del y becomes del u by del y times square root alpha, and then del 2 u by del y square becomes alpha times del 2 u by del capital Y square. Okay, I'm just using the chain rule here. So since you have del u by del t equals nu del 2 u by del y square, you can substitute these values and you will see that even with the scaled variables the equation is satisfied. Okay, even with the scaled variables the equation is satisfied, the scaled independent variables. That means that if you have, let's say this is your y comma t plane, if there is a solution, if at this point you have a solution, you have a value, okay, at y comma t, let us say you have a value which satisfies this equation. Okay, so it's not just a value that will satisfy the equation, you will need a derivative, both derivatives, right? So at y comma t you have the time and spatial derivatives such that this equation is satisfied. Then what this is trying to tell us is that when you take this y to square root alpha times y and t to alpha times t, let us say alpha is greater than 1, then this function also, the values of derivatives at this point also satisfy the equation. That means there is a sort of a parabola over which you can define the values of these derivatives. So in a way, second argument over first argument squared, if this remains constant, then you can say that the values of these derivatives are remaining constant, they are satisfying each this governing equation. Okay, and taking help from this intuition, what we say is, I am not going to find a solution u y t, I am going to find a solution where, actually hold on, yeah, instead of finding u y t, I am going to find a solution f of eta, where this eta is defined as y over some constant times square root of t. Okay. So this intuition, again, I'm giving you an intuition. You don't need to know this for this course, how to get this intuition. If I ask you a similarity solution problem in an exam, I will give you this guess. I will give you what is the similarity variable that you should start with. Okay. So this is called the similarity variable, and this is called similarity ansatz, which is from a German word which means a guess. Okay. So this ansatz and similarity variable I will give to you in the exams. You have to, you should be able to visualize it, but you don't need to derive it from the first principles. Okay. Yes.
What is the second argument, first argument square is constant?
So what I am saying here is if you have t by y square. So second argument by first argument square, if you maintain that as a constant value, then the value or the value of derivatives of this function don't change, because this thing is satisfying the governing equation as it is. Okay. So on this parabola, it looks like the value of derivatives, they satisfy this governing equation. Okay. So it's like instead of the solution being a function of y and t separately, the solution is a function of where you are on this parabola. Okay. The solution u is a function of where you are on this parabola instead of it being a function of y and t arbitrarily. Okay. It matters where you are on this parabola to the solution, or not just this parabola, actually there are parabolic lines, and what it means is that in a way you can calculate, let us say I ask you, okay, what is the solution at this y and at this time. What you can do is you can make a parabola and you can tell some information of this solution just by looking at this parabola. Okay. These are not exactly characteristic lines, but when we look at first order PDEs, this is what the motivation of characteristic lines is, but these are not characteristic lines, so to say.
So what is C?
C is some arbitrary constant. Yeah, of course. That constant is arbitrary. That constant doesn't have to be the same value. Basically, for any constant, you can write this as the ansatz. And now we will try to substitute and see what we get. So if I have u of y comma t, I am writing it as f of eta, then del u by del t is f prime. So this prime I am going to use to denote df by d eta, okay, times del eta over del t. Eta is defined like this. So what does this become? F prime y by c 1 by root t. What is the derivative? Minus half t to the power 3 by 2. Okay. What is del u by del y? It is f prime times del eta by del y, which is this guy, and del 2 u by del y square becomes f double prime over c square t. Okay. Now substituting this in our governing equation, we have del u by del t equals nu del 2 u by del y square, which means minus half f prime by c t to the power 3 by 2 equals nu times f double prime by c square times t. There is a y also here. Okay, one c cancels out, one t cancels out, so this becomes a half. So what do we get? We get f double prime plus y by 2 nu root t or cy by 2 nu root t times f prime equals 0. But y by root t we know is eta times c. Okay, y by root t we know is eta times c. So this means f double prime plus y by root t is eta times c. So c square eta over 2 nu f prime equals 0. And this is the first sign of, so if you get this, what is the peculiar thing about this? What have we done? What is this result? This is an ODE. Okay, we have managed to convert a PDE into an ODE. We have managed to convert a PDE into an ODE, and this is the first sign that the similarity variable and the ansatz that you took are going to work. The reason why I say this is the first sign is because we still have boundary conditions to deal with. Okay. So, we will see if we are left with, so these are 3 boundary plus initial conditions for the PDE. If these 3 somehow get reduced to 2 conditions for the ODE, then our closed system becomes another closed system and we have no problems. Okay. So, these 2 are the major steps in determining if your ansatz and the similarity variable that you are taking and the ansatz, if they are correct. Okay. As we move further down in the course, we will see that using these as conditions, we can derive what is the correct similarity variable. Okay. What I could have done here is I could have taken eta to be some y by c t to the power alpha. Okay, I could have taken eta to be that, done all this algebra and said that only when alpha equals half, this is an ODE, so alpha should be equal to half, and that's when we will get a similarity solution. Okay. Now, a major point that I want to pinpoint here is that these are linear PDEs. We are doing some tricks and we are getting to a solution. For linear PDEs, the uniqueness of solutions is guaranteed. So, if we find a solution, that is the solution. Okay, that is why all of these tricks you can make them work. You can try different methodologies, and whichever one results in a solution, you can say, okay, I have found the solution, because these are linear PDEs. You could not do this for a non-linear PDE because a non-linear equation has many solutions. Okay. So, if I eventually end up solving the system, make a closed system and solve it, then that is the solution. This is an ODE. You will not get an ODE. So, try this at your home. Do this algebra for alpha equals 1 by 3. You will still have y and t's remaining here, and you will not be able to combine them into an eta. Half of the step, half of the, like with 50% confidence, you can say yes, assumption was correct. We still have boundary conditions to deal with. If we get ODE from PD, we are on the right track. Let's look at the boundary conditions. That's how you should interpret it in your head. So we have f double prime plus c square eta over 2 nu times f prime equals 0. Let us look at the boundary conditions. Y equal to 0 for any t, what is eta? Y equal to 0 any time, what is eta? 0. So, u for y equal to 0, t is u naught, means f of eta equals 0 is u naught. U for y tends to infinity for any time equals 0. What does it mean? F of eta tends to infinity is 0. And now let us look at the initial condition, and what I am going to do is, instead of writing u y comma t equal to 0, I am going to say u y comma t tends to 0 is also equal to 0. This limit is defined, okay, which means again f of eta tends to infinity equals 0. So, you see two conditions, one boundary and one initial condition, they have collapsed into a single condition for f. So, eventually you had three conditions, you had a PDE, you are left with a second order ODE with two conditions. From a closed system you have went to another closed system. So, our similarity guess and the similarity variable are correct. You can proceed to solve this equation and you will find a solution, and that will be the solution because this is a linear PDE. Okay. Now, as it turns out, so this is your equation that you have to solve. This is the equation that you have to solve, and these are the conditions that at 0 it is u naught, and at eta tends to infinity this is 0. Okay. This can be an exercise for you guys, that this solution, eventually the solution that we find is not going to be dependent on this variable c. Okay, it is not going to be dependent on this arbitrary constant, not variable, arbitrary constant c anymore. Okay. So, I'll leave it up to you guys to verify that. You can do the whole algebra that we are going to do, not assuming a specific value for c. What I am going to do here is that I am going to take that c is 2 times square root of nu for making my algebra and writing simpler. Okay. So, when I take this, so take this and then verify that solution is independent of c. So, we are taking this for the value of c. So, c square is 4 times nu. So, we get f double prime plus 2 eta f prime equals 0. What is the solution of this? So, this is f double prime by f prime is minus 2 eta. This means, what is the solution? Huh? Solve this ODE. F double prime by f prime is minus 2 eta. This means f prime is what? E minus eta square with some arbitrary constant multiplied. So, let us say some a e to the power minus eta square. That is the solution of this equation, right? And so, if f prime is this, so we have df over d eta equals a e to the power minus eta square. This means I can take df integral and I can write it like this. I can write this integration from 0 to eta, and here what is f at eta equals 0? It is u naught. So, I can write it like this. So, this means f minus u naught equals integral from 0 to eta e to the power minus let's not write the same variable here. It is e to the power minus, let's write it as e to the power minus s square ds times the constant a. Okay. I mean, I could have written it like some other variable here, let's say some capital S, and this is f of capital S, then I'm swapping the variables. Okay. This is what you get for f at eta. So f of eta is u naught plus a 0 to eta e to the power minus s square ds. So we have already used this condition that f of eta equals 0 is u naught. The other condition that we can use is for eta tends to infinity, this value is 0. So eta tends to infinity, which is 0, equals u naught plus a 0 to infinity e to the power minus s square ds. So from here we can get the value of a, which is minus u naught over 0 to infinity e to the power minus s square ds. What is the value of this integral? Does anyone know how to calculate it? How do we evaluate this integral? Huh? So we can evaluate this integral like this. So let's say I is this guy. Okay, then what we can say is I square is going to be plus some, let's say t square, this is not time, ds dt. Okay, that is what my I square is. And now this is what? This is an integral ds dt from 0 to infinity, 0 to infinity. This is an integration in the first quadrant. In the whole first quadrant, this is an integration. And here you can change the integration variables from Cartesian to polar coordinates, and you can write that I square is going to be, so s square plus t square is some minus r square. ds dt is the area element, which becomes r dr d theta. Okay, and then theta is varying in the first quadrant, theta is varying from 0 to pi by 2, and r is varying from 0 to infinity. Okay, so I square becomes pi by 2 times 0 to infinity e to the power minus r square r dr, which becomes what? So what is this integral? E to the power minus r square r dr. What is this integral? Hmm? What is this integral? You guys will have to do these things a lot in exams. Okay, so it's better to practice right now than delaying it. What is e to the power minus r square r dr? R square, you assume some variable, then 2 r dr is that d times that variable, d of that variable. You bring 2, multiply, divide by 2. So this becomes pi by 4. Okay, this whole thing, this integral will be 1 by 2. So this means I is root pi by 2. Okay, so a is minus 2 u naught over root pi. And now we have found our f of eta. We have found our f of eta, from which we can find u y t, they are equal. So f of eta is u naught times 1 minus 2 by root pi integration 0 to eta e to the power minus s square ds. So u of y comma t is u naught 1 minus 2 by root pi. What was eta? Eta was y by c root t. So y by 2 root nu t, and this is your solution. Okay. Now you see an interesting quantity appearing here, and that is this y by root nu t. Okay, this y by root nu t that is appearing in this solution. What are the dimensions of this? First of all, what are the dimensions of nu? So if I was writing del u by del t equals nu times del 2 u by del y square, what are the dimensions of nu? Kinematic viscosity, that is meter square per second. So by that, what are the dimensions of y by root nu t? This is a dimensionless number. So root nu t has the units of dimension, length basically. It's a length. Root nu t is a length. Intuitively, what does this length mean? What does this root nu t mean? Intuitively, what does this root nu t mean? It means the length to which the diffusion has taken place over time t. What this means is, so we had a plate that started to move with u naught and the fluid above it was at rest. So what this length intuitively means is that approximately after time t has gone over, approximately over length nu t, so this, let us say delta over nu t, you would start feeling the effect of the plate. If you are far away from delta nu, far away from delta or far away from square root nu t, for example, let's say nu is 10 to the power minus 6. Okay, let's say nu is 10 to the power minus 6, and we are looking after 100 seconds. Okay, nu is 10 to the power minus 6. We are looking after 100 seconds. What is square root of nu t in that case? 10 to the power minus 2. So if you are at 1 centimeter above the plate, you will start feeling the effect of the plate. But if someone was telling you, okay, what if I am above 1 meter above the plate, you would not feel the effect of plate. That is the value, or that is the intuitive value of this root nu t. It is the length at which you start feeling the plate or effect of the plate after time t. If someone gives you an experimental data and says, okay, at 1 meter at t equal to 100, I started seeing some oscillations, you will say your data is nonsense, because I cannot start feeling the effect of the plate so early at such a distance. Okay, it's sort of like it's giving you an intuition of how fast the effect of plate is being felt through diffusion. There is no wave propagation here, this is through diffusion. Okay, yeah.
Can you please explain the conversion from coordinate to polar coordinate, Cartesian to polar coordinates of that I square?
This integral is this one, no? So let's say this is s, this is t, you are integrating 0 to infinity, 0 to infinity. So you are integrating in the first quadrant. Over the whole first quadrant you are integrating. So instead of writing like this, you can take integral elements like this, where you are writing r dr times d theta, or dr times r d theta is the element, and the first quadrant limits will be from 0 to pi by 2 and 0 to infinity. Okay, so that is the intuition behind the square root of nu t, that we are trying to estimate at what length would I feel the effect of this plate after some time t has passed. Any other questions? So if there are no questions, we'll move forward. I'll just introduce that particular problem that we are going to look at. Yes.
That the dimension was equal to length. Orientation, or is there a deeper?
So that's a good question. That just because square root nu t is of dimensions length, how does it mean that it is the approximate? Okay, that's a good question. So this I will answer when we go to non-dimensionalization or dimensional analysis. That there is a concept of a characteristic scales of the problem. Okay, there is a concept of characteristic scales of the problem, and that means using whatever variables that the problem depends on or parameters that the problem depends on. If you can formulate some scales, then those scales carry some meaning. Okay. So what is the what is the meaning of this square root of nu t is that what you can think about it as when y by root nu t. So this is the variable, this y by root nu t is the, let us say, dimensionless length to which you have to integrate, or half of that to which you have to integrate. Okay. Now you can think of y by root nu t being very high. What is happening to this? When y by root nu t is very high, what is happening to this 1 minus this function? So if you look at the plot of this function, just the one inside the brackets, for y by root nu t equals 0, this function is 1. Okay. For y by root nu t tends to infinity, this function is 0. Okay. So basically what I am saying is that as you increase y by root nu t, the effect of the plate which is being given by this velocity is reducing. That is the only additional explanation that I can offer at this moment, that the effect of the plate is reducing as I am moving ahead in y by root nu t. So root nu t carries that meaning that 5 root nu t, 10 root nu t, or 20, 200, 1000 times root nu t, you will be seeing lesser and lesser effect of velocity, plate, lesser and lesser effect of plate. And this, so this function is usually called the complementary error function of this eta. Okay, this is ERFC, usually written in the literature. We'll do the next problem on Friday.